You very much for the introduction and for the invitation to speak in this seminar. It's a real pleasure to be here. So I'm going to be talking about joint work with Alexander Pascadi, and also some joint work of mine with the sieve Zaman is going to make its way into the presentation. So I'm going to be talking about the GLN large sieve. This is a very vibrant area of number theory that has a lot of ongoing research. And I guess in the event that you haven't seen a large sieve before, let's start at the beginning. So the large sieve was something that was originally proved for characters, for abelian characters. So I'll state the version that was established for Dirichlet characters. So for positive integer q, I let chi mod q be a Dirichlet character for the group z mod q z star. And for z mod q z star, this abelian group, we have the following statement of character orthogonality. So if the GCD of A and Q is 1, then I can express the indicator function for this residue class, evaluated at n, as this linear combination of the characters chi modulo q. All right, so character orthogonality comes up in all sorts of settings. And one thing that has shown itself to be very important throughout analytic number theory is to have a notion of character orthogonality to varying moduli. And so what one could do is one could, on the one hand, embed the characters chi mod q and the characters chi mod q prime into a larger group, z mod q q prime star, but then you've inflated the conductors of all of the characters. You've inflated the modulus for the group, and we want to establish some kind of notion of orthogonality that holds without inflating the modulus. And we can do this, but only in an approximate sense. And it's this approximate sense that we call the large sieve inequality, which I'll state in the following form. So I have a sum over moduli little q going up to big Q, and then I sum over all primitive chi modulo q. And then what am I summing? I'm summing the modulus squared of the sum over little n going up to big N of chi of n b of n. And instead of having an equality like I do for character orthogonality to a specific modulus, I'm only going to have an upper bound for this because I'm only able to establish an approximate form of orthogonality. And this is the upper bound that we achieve. Now, just so that we have a sense of how strong this is, the Cauchy-Schwarz inequality would have us replace n plus q squared with n times q squared. So this is a pretty massive win. And a few notes about it. The restriction to chi primitive is actually quite important. So if I have a chi modulo little q, I could sort of think of that character as being a character to a modulus d times little q for any positive integer d, and in that sense, the character on the higher modulus is imprimitive. I want the conductor to be I want the modulus to be minimal in this sense. The second thing is that this bound over here, this n plus q squared minus 1, is sharp. If I want the function b here to be arbitrary, then this is the best upper bound that we can have. All right. I'm going to dress this up slightly differently. So let's have frac F1 be the set of all primitive Dirichlet characters with F1 here with this appendage of Q, meaning I'm chopping off my primitive characters to have a conductor going up to big Q. All right, so it's like a truncated family. We actually know how large this truncated family is. Again, all the characters that I'm considering here, I want them to be primitive. All right, so we can count these characters. And now I'm going to state the large sieve in a slightly weaker form. So I can consider my function b here, and I really want to think of the left-hand side of my large sieve inequality here to be supremum over my functions b, such that the square of its L2 norm is 1. And um, I'm now summing over my primitive chi running through f1 of q, summing this same modulus square. And now my right-hand side, because I'm taking my supremum over the L2 norm of b equaling 1, I get n plus the size of my truncated family. All right. So again, Cauchy-Schwarz is going to only give us the trivial bound of n plus the size of the truncated family. And so this is a fairly massive win. I can think of the left-hand side here as being the operator norm for a matrix A that I'm sorry, for the matrix A star A given as follows. Well, I construct A by considering entries chi of n. So chi is ranging through my truncated family and little n is going up to big N. I form a matrix from this. And then I look at the matrix A star A and its operator norm, or its largest eigenvalue. The large sieve inequality is telling me that this is that this largest eigenvalue is bounded from above by n plus the size of the family. Okay, so this this bound is ubiquitous throughout analytic number theory. It comes up in many different places. Here's a small sampling of them. So this is key for the proof of the Bombay-Vinograd theorem, which tells us that primes in arithmetic progressions are very well equidistributed on average to moduli q, as q varies up to x to the half plus epsilon. The large sieve inequality will help us to get optimal bounds on moments of Dirichlet L-functions at the central point 1/2, all the way up to the 8th moment. And we also see the large sieve inequality making an appearance when we establish zero density estimates, trying to understand how infrequently Dirichlet L-functions violate the generalized Riemann hypothesis. So given how central the large sieve inequality is for Dirichlet characters to analytic number theory, we might want to figure out how we might extend the large sieve in other settings. And there are a number of ways that we can do this. I'm going to focus on one today. So for an integer m at least 1, I'm going to let frac m be the set of unitarily normalized cuspidal automorphic representations pi of GLN over the rational field. Everything that I say in this talk is going to actually carry over fields other than the number fields other than the rationals, but for notational simplicity, I'll just stick to the I'll just stick to the rationals today. And I'm going to consider each representation pi in this set to be normalized so that its central character is trivial on the positive reals. I'll say in a little bit why this is such an important hypothesis for what I'm about to describe. Okay. The Sataka isomorphism.
I'm sorry about the first definition. Where does M, is it GLM maybe
Oh,
in the
yes, I'm sorry.
definition?
GLM. Yes. Thank you. Sorry about that. So the Sataka isomorphism does the following for us. So we can express pi as a restricted tensor product over all places of Q of pi p, where pi p is a smooth admissible representation of GLM of QP, where I think of Q infinity as being R. And um, if P is a finite place, so it's corresponding with a prime, and it doesn't divide the conductor, then the Sakai isomorphism relates to pi p, a semi-simple conjugacy class in GLM of C, represented by this diagonal matrix, where these numbers alpha 1 through alpha m are complex numbers. And for p, so this works for all p not dividing the conductor of pi. For p dividing the conductor of pi, well, I do end up having a similar sort of matrix, but it's no longer in GLM of C. I might have some of these alphas equaling 0. And from this, we can read off the standard L function for pi, which I write as ls pi. And it's given to us by an Euler product. And this Euler product is a product over primes p. And for each prime p, I look at the reciprocal of my characteristic polynomial for a pi of p, be it in the case where p divides q pi or not. And this Euler product, it expands out as a Dirichlet series, which I write as a sum from n equals 1 to infinity of lambda pi of n over n to the s. Lambda pi of n here is the nth Hecke eigenvalue of pi. And this converges absolutely for real part of s bigger than 1. All right. So the q pi here is the conductor of pi. And so in particular, at each p dividing q pi, pi p is ramified. All right. We write the completed L function like this. So I might have to address some a possible pole at s equals 1 in the event that pi is the trivial representation for GL1. And then I have q pi to the power s over 2, my Euler product ls pi, and the L function associated to pi infinity, well, this is going to be given by a product of gamma functions. All right. So we know that this completed L function, as I've given it, is entire. And it also satisfies the functional equation relating ls pi to L of 1 minus s comma pi tilde, where pi tilde is the dual of pi. And from this completed L function, we can read off the analytic conductor, first defined by in the manner defined by Ivanit and Sarnak, where I take the conductor q pi times a contribution from all of the Langlands parameters that are arising in these gamma functions. And this gives us a measure of the arithmetic and spectral complexity of pi. And so when we make estimates for automorphic L functions, we want things to be as uniform in the analytic conductors we can manage. Okay. So the normalization for the central characters that I gave before, it only exists to ensure that if I were to take the collection of pi in frac m and truncate things so that I only consider the pi with analytic conductor going up to q, that this set is in fact finite. Okay. So now let's take S, a finite subset of frac Fm, and let Q be the largest analytic conductor out of all of the pi in our set S. So what we might hope to prove is a direct analog of the large sieve inequality for Dirichlet characters. And that would look something kind of like this, although I'm giving myself a little bit of wiggle room here with permitting a possible factor here of nq to the epsilon. So we would take a supremum over all functions b from the naturals to the complex numbers with L to norm equal to 1. We sum over all pi in our family. We sum over little n going up to big N. And instead of characters here, we have our nth Hecke eigenvalue of pi. And the best sort of quasi-orthogonality that we might be able to obtain for this family would be, ignoring the nq to the epsilon, would be n times the size of the family. And so again, you can think of a matrix A constructed by taking entries lambda pi of n, where pi is varying in your family S, and n is varying up to big N. You look at the matrix A star A, and you want to bound for its largest eigenvalue. And the best that you could hope for is a bound like this. Okay. And well, this is the best that you could hope for. What's the trivial bound that we're trying to beat? It's simply the bound that comes from Cauchy-Schwarz. Instead of n plus size of S, we would have n times size of S. So this is the threshold that we're trying to beat, and we're trying to make it all the way to here. Now, this is our goal, but interestingly enough, while it is often achievable, it is not always achievable. So first, here are a couple of examples where this goal is provably not in the cards for us. So first, there's the work of Ivanitz and Lee, which tells us that if we look at the family of pi on GL2 that are associated to the new forms on gamma 1 of q of weight k, we can think of k as being fixed and q as being large. Then in addition to the n plus size of S here, there would be another sizable term. Another sizable term that's genuinely present. Another situation where this idealized quasi-orthogonality is just provably not in the cards for us is in the large sieve inequality, not for all Dirichlet characters, but for cubic Dirichlet characters. This was originally studied, originally studied. This was studied by Roger Heath Brown, and in addition to the in addition to the n plus the size of the family, there is also a term that was kind of like n plus size of the family plus n size of the family to the 2/3. And um, and that term, at least under the generalized Riemann hypothesis, is genuinely there. It's unavoidable. And this was established by Dunn and Radziwill in 2024. So there are a few instances where this idealized quasi-orthogonality is just not in the cards, but a lot of the times it is in the cards for us. So if I fix a level Q and I look at the family of pi on GL2 corresponding with Hecke new forms, I can restrict to holomorphic or Moss. And I average over the spectral parameter, either being the weight or the Laplace eigenvalue going up to big Q, then the goal is in fact achievable. Right? Again, this is due to the foundational work of Desvillers and Iwaniec in 1982. I don't want to try to give a complete history here, but a few recent highlights. There's work of Subhajit Jana from 2021, which gives a very nice generalization of the work of Desvillers and Iwaniec. I'm giving a special case here. He actually proves something slightly more general than what I'm saying. But you can look at the pi corresponding to Hecke-Moss cusp forms on SLMZ with analytic conductor going up to Q. And in this situation, optimal quasi-orthogonality is proved provided that n is small relative to big Q. So in a range, but this is a crucial range for a lot of applications. And a similar sort of result holds in the level aspect. This is work of Blomer. And now in this aspect, I'm looking at the Hecke-Moss new forms on gamma naught of Q. I'm thinking of their Laplace eigenvalues as being absolutely bounded. And in this situation, we're now looking at things in the Q aspect. Q is governing the analytic conductor here. And so now the goal is true, provided, again, that the length of the large sieve is small relative to Q. There's a lot of work on this in the past, a lot of ongoing work. I don't want to try to give a complete history. But there is a common denominator amongst all of these results that I would like to point out. And the common denominator amongst these results is that in each of these settings, pi is automorphic with respect to a single group. Right? The group of automorphy in each of these examples is fixed. And that is crucial because it means that each of these results are amenable to trace formula techniques. But if you look at the large sieve for Dirichlet characters, the group for each character, Z mod QZ star, it's moving. It's not fixed. Right? We're looking at these groups over little q going up to big Q. And that means that, well, it's unclear at this point whether trace formula methods are going to be helpful with averaging over groups. So in the simplest example that I can think of at least, one can consider the family of GL2 automorphic forms S corresponding with non-CM elliptic curves by modularity with square free conductor going up to big Q. So, so with this, uh, you're looking at several subfamilies transforming under gamma naught of, well, the conductor of the elliptic curve. And so we have several different groups that we're considering within this family, and trace formula methods do not seem uh, to be able to handle this particular family. And there are other sorts of families that one might want to consider um, where the group of automorphy is moving. And now, in order to address this particular family of non-CM elliptic curves with varying square-free conductor going up to some universal threshold, Duke and Kowalski in 2000 came up with another route that doesn't use trace formula methods, but instead it's rooted in the duality principle. This alternate method is capable of handling arbitrary subsets of mathfrak f of m. But here, we won't be able to achieve the goal unless the length of the large sieve is large as a function of the size of the family and the largest analytic conductor. So for this talk, I'm going to focus on S being the universal truncated family. All right, if you can handle this family, then you can handle almost any other. All right, so in these other results, I'm sorry, in the work of Duke and Kowalski, and also in my work with Zaman, the generalized Ramanujan conjecture plays a pretty big role. So that is a statement about the size of these parameters alpha, j, pi of p that show up in the Euler product factorization of ls pi. For this, I define theta m to be the supremum over all pi in Fm and over all primes p and over all j going from 1 up to m of log of this local parameter divided by log p. All right, so this is asking within my family, how large are these parameters that show up in our Euler product? The generalized Ramanujan conjecture asserts that if m is at least 2, then theta m is just 0. So all of these parameters in the Euler products are just bounded by 1. And if I look at a p, if I look at a p not dividing the conductor, then uh, then these local roots should just equal 1. All right. So the generalized Ramanujan conjecture is this. We only know it in a handful of special cases. This is the best bound that we know in full generality, that theta m is slightly less than 1/2 with a savings that's decaying with m. Okay, so this is due to Luo, Rudnick, and Sarnak. They handle the p not dividing the conductor, and then for p dividing the conductor, there's additional input from Mueller and Spey.
Sorry, just to interrupt you. Henrik has a question. Henrik, would you like to unmute?
Yes?
So the question is, do small primes take part in your definition of theta? Thank you, Henrik.
No, they don't. This is supposed to be a universal bound.
Yeah, but it's sup, so not supreme. So if p equal to 2 would be there.
Ah, okay. I see what you're saying. So in the event that
I think it's sublime, right?
yes.
Yeah.
Yes. Thank you for that. should be limb soup, yes. Okay. So what Duke and Kowalski proved in 2000, and I'm going to include in my discussion of this a small upgrade that comes from recent work of Yujiao Jiang. We obtained the following result. So this is the left-hand side of the large sieve inequality that we want to establish for frac M of Q. And what they established is the following bound. So the n part of the so let's keep in mind what the goal is. The goal is n plus the size of the truncated family. And so how far off are we from that? We're off by this factor. N plus n to the power half plus theta m. And because of the bounds on theta m from before, this exponent is strictly less than 1. And then there's a power of q that we have to worry about. So this matches our goal when n is suitably large. But suitably large means, well, I have to know what theta m is, and I have to know what the size of my family is. So under the generalized Ramanujan conjecture, the theta m is 0, and we have achieved our goal when big N is in this range. Now, I could take the bound theta m is less than or equal to 1/2 minus 1 over m squared plus 1. I can insert that in for here, and then we get this bound. But this m squared plus 1 exponent is quite large, and so in order to have a good understanding what's going on, I need to know how large my family is. We don't have asymptotics for the size of the universal truncated family, but we have polynomial upper and lower bounds. And we expect the lower bound, which is due to Brumley and Milosevic, we expect the lower bound to be the true order of magnitude, and the best that we can do in the way of an upper bound was established by Brumley, myself, and Zaman. And so what we'd like to be able to do is establish our goal of perfect quasi-orthogonality in a wider range of big N. Okay, so here's the work of Duke, Kowalski, and Jiang. My work with Asif Zaman also considers this problem. We, for technical reasons, have to insert this GCD condition into our sum. We can only consider the little n that are coprime to q pi, the conductor of pi, as pi varies in the family. And we get a slightly different bound. There's no n dependence on the second term on the right-hand side. There's just this power of q. But this power of q could be quite large if my Ramanujan exponent is also large. Right? So for this second result, this matches our goal in this range, and it's tough to compare these ranges because I don't really know what theta m is. I expect it to be 0, and I don't really know how large the size of the truncated universal family is. I expect it to be q to the m plus 1, but it could be a bit larger. So my work with Alex Pascadi gives an improvement over the work with over my work with Zaman by removing the dependence on the Ramanujan exponent, and it also removes the GCD constraint. So this is my main result with Pascadi. We established this large sieve inequality with n plus size of the truncated family times q to the m. So there's no theta m dependence anymore. And also there's no GCD constraint anymore. So this matches the goal when n is at least q to the m times the size of the universal family. And the nice thing about this result is that compared to the previous two results, well, maybe there's a range of n in which Duke, Kowalski, and Jiang, or my work with Zaman, maybe it might be trivial relative to what Cauchy-Schwarz gives. We'll assume first that it's non-trivial. In the event that n is suitably large, then either of these results is optimal. But let's assume that we're non-trivial and n is not so large that either of these results are optimal, right? So n is smaller than this or smaller than this. Well, whenever they're both non-trivial and non-optimal, our new theorem gives an improvement. So I'm going to briefly discuss one application. There are several others. So this gives a new bound for the second moment of L½ pi as pi varies in the truncated universal family. This can be used for zero density estimates to count possible violation, to bound the number of violations for the generalized Riemann hypothesis for L functions near the one line. And it can also be used to establish density estimates counting possible violations to the generalized Ramanujan conjecture. I'm just going to focus on the second moment for L½ All right. So for a family Fm of Q, it could be the case that the generalized Ramanujan conjecture is satisfied for each pi in our family, and I could possibly assume that the B of n is supported on square-free integers. And if I have these two things, then it's a fairly straightforward consequence of Holder's inequality that if k at least 1 is an integer, then I can get this variant of our large sieve inequality. So if I take k equals 1, I recover the right-hand side of the large sieve inequality that was in the theorem statement from before. But using a delicate combinatorial argument, what Pascadi and I can show is that this bound actually holds unconditionally for all integers k at least 1. I don't have time to go through the argument, but let's see what happens when we use this Holder inequality for an optimal choice of k. Well, we have the approximate functional equation, so we can establish a bound on L½ pi absolute value squared in terms of a partial sum of my nth Hecke eigenvalue divided by square root of n. And in light of this, we might want to show that L½ pi absolute value squared is small on average. And to do this, in light of the approximate functional equation, I might want to take my large sieve inequality and have it be applicable with n being roughly q to the half plus epsilon, and I want um, for this um, for this particular value of n, I want my large sieve inequality to at least be trivial. And now if I write delta for log of size of family divided by log of q, then I can choose k optimally for this particular choice of n to be 2 times the quantity little m plus delta. And really, I only want a lower bound for delta. And in light of the lower bound on the size of the universal family by Brumley and Milosevich, I can take I can think of delta here as being m plus 1. And so now applying the large sieve inequality for this particular choice of B of n, what we're able to establish is that this is bounded from above by again, I'm relying on delta here being log size of family divided by log of q. I get this upper bound, but q to the delta is just the size of the family. All right. So I'm being a little cavalier with some of the analysis here because I need to be careful about my application of dyadic summation here. But again, as q is approaching infinity, delta is settling somewhere between m plus 1 and 2m. And well, this fraction is only getting worse as delta gets smaller, so I may as well assume that delta is closer to m plus 1, and this gives us an upper bound for the second moment of L functions in our family, and that is given to us by this. All right, so I'm normalizing for the size of the family here, and we're left with q to the power 1/4 minus 1 over 8m plus 4. So this is actually a new bound for all m at least 2. But why is this a meaningful bound? Well, let's take into account the fact that the generalized Riemann hypothesis implies that L of a half pi is bounded by analytic conductor to the power epsilon. The convexity bound, which you can think of as being a trivial bound of sorts, is analytic conductor to the 1/4. And in a spectacular breakthrough made a few years ago by Nelson, if you assume a technical condition called uniform parameter growth, which is saying something about the particular manner in which the analytic conductor varies in the family, then we obtain only a small power savings over the convexity bound. This is quite a small savings as m gets large, but this savings obviously is very, very hard fought. And if I don't want to assume parameter growth, then all I can do is save a small power of the logarithm of the analytic conductor of pi over the trivial bound. And what this L2 moment is saying is, just as an application of Chebyshev's inequality, is that with a power saving number of exceptions, I have to have that my central value is bounded from above by analytic conductor to the power 1/7. So the savings here is completely independent of in contrast with, for example, what Nelson proved, the savings here is independent of M. It's an absolute savings over the convexity bound 1/4, and we obtain this almost always. Okay. Maybe I'll try in the few minutes that I have left to talk a little bit about the proof. I'll skip over some details. So in Duk-Kowalski, what happens is one applies the duality principle to this. And so we're looking at this as the operator norm of a matrix A star A, kind of like what I was saying before. And we then apply the duality principle. We're then able to relate this. This is in fact the supremum over all functions beta, going from my truncated universal family to the complex numbers with L2 norm 1 of this. And I can replace the truncated sum over n with a smooth approximate. Duke and Kowalski expand the square and swap the order of summation. And that reduces the issue to computing sums of this sort. And in order to compute sums of this sort, I need to understand properties of Rankin Selberg L-functions. And so these are built as Euler products arising from the parameters at P for pi and the parameters at P for pi prime. These Rankin Selberg L-functions are absolutely convergent for real part of S bigger than 1. They analytically continue to all the complex plane apart from a possible pole when pi equals pi prime here. And satisfies the functional equation relating S to 1 minus S. We have a convexity bound, so we can estimate these Rankin Selberg L-functions inside of the critical strip. And we can bound the analytic conductor for these Rankin Selberg L-functions in terms of the analytic conductors for pi and pi prime. So now I can get to the heart of the matter. So here's our exponent towards Ramanujan from before, where all these soups are replaced with lim soup, as was pointed out earlier. And what Duke and Kowalski show is that there's a function, I'm sorry, Duke Kowalski and with this new input from Yu Jiaojiang, there is a function h of pi, pi prime, and s, holomorphic and absolutely bounded in this region with the property that the Dirichlet series formed by the coefficients that I'm actually looking at, well, these are this Dirichlet series is actually factorable as my bounded function times my Rankin Selberg L-function. And so now I can apply Mellin inversion. I get this. And then I push the contour to the line real part of S equals a half plus theta m plus epsilon. Pushing the contour, I get a contribution from the pole at S equals 1 in the event that pi equals pi prime. And then I estimate everything else using the convexity bound. Now, I'll try to get through this in just a few minutes. So on in my work with Zaman, we begin on the dual side as Duke and Kowalski did. But unlike Duke and Kowalski, we don't open up the square. So to describe what happens here, we have our Rankin Selberg L-function. Here's our Pth Euler factor. I'm going to jump ahead a little bit. The point here is that as long as P does not divide the product of the conductors, we can, within the Pth Euler factor, we can separate the contribution from the local parameters coming from pi and the local parameters coming from pi prime using orthogonality of Schur polynomials. And, well, using this orthogonality of Schur polynomials, what we are able to do for each n, as long as we insert these GCD conditions, we can establish this this inequality for each n. And then we sum both sides of this over all n. And now we have a contour integral involving the Rankin Selberg L-function. And in order to handle these GCD constraints, we have to separately discard the contribution from the Euler factors arising from the ramified primes. So now there's no function h of s that only is holomorphic in a certain half plane. But the downside is that in order to estimate the contribution from the ramified Euler factors, we need the Liouvre-Nixarnik bound. And that is an inefficient bound to apply here. That's why in the Thorner-Zaman version of the large sieve inequality, we had this contribution from the Ramanujan bound, because that's how we handle the contribution from the primes here. So I know I'm a little bit over. Thank you for your patience. So very, very briefly, I will say that in my work with Pascadi, we eliminate the need for any GCD conditions that might arise from our application of Schur orthogonality. And this requires for us to treat the n arising from primes dividing the conductor of pi and pi prime. We have to handle these quite a bit more efficiently. And this actually can be described in terms of a certain linear algebraic formulation, which I'll just briefly say as saying that so in order to establish this without any sort of GCD condition, we established that for a given n, the matrix in pi and pi prime varying in our family, the matrix that arises from these numbers here form a positive semi-definite matrix. And thank you for your time and attention. That does it for today.